Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I record all of my lectures. And so what I'm going to do today is this is going to be a walkthrough of all of the steps that you need in order to calculate a directional variogram and model it with a full multi-directional, two-dimensional, positive definite model that you can use for kriging or simulation. There's so many different things that you can do with a variogram. It's a powerful predictive tool and a tool to just understand spatial continuity. Now, if you want to follow along with this, just go ahead to my GitHub account, github.com, GeoStatsGuy, and I have a bunch of repositories. And there is this repository right here, Python numerical demos. And if you go there, what you're going to find is a list of many demonstrations. And there's some new interactive ones where I use IPy widgets and matplotlib to automate things so that you can play with the methodologies and visualize the result immediately. It's called Interactive Variogram Modeling, IPython Notebook, IPYNB. And so go ahead and download that. Now, you will also need a data set, but no worries, that's available to you too. There's another repository called, right down here, GeoDatasets. Now in this directory, there's a whole bunch of data sets you can work with. And so the data set that we'll use is right down there. And you can go ahead and work with that. Okay, and I'm going to walk you through the workflow and show you all of the steps and help you so that you can take this workflow, open up your own data set, and go ahead and calculate and model two-dimensional variograms. So I think this will be really helpful to you. I specifically coded this yesterday for my students because I had just assigned or was about to assign a variogram modeling assignment. I thought it'd be really cool for my students to be able to have a nice interactive workflow to get experiential learning about variogram modeling rather than something kind of ad hoc where you change a parameter, run, change a parameter, run. I want them to be able to visualize and see the impact of their choices immediately. I think that's very powerful. Okay, so every time I do one of these workflows, I like to put some documentation up front so it's self-contained. It contains some of the information from my typical lecture notes. If you go ahead and look on my YouTube channel, you'll find that there's a bunch of videos here available to you. There's a playlist specifically for this course, Data Analytics and Geostatistics. If you view the entire playlist, you'll find that there are lectures right down here on spatial bias, spatial declustering, also stationarity, spatial continuity, variograms, variogram calculation, variogram parameters. There's a lot of lectures here available to support you. Okay, so the variogram, so what we want to do is calculate the experimental variogram, and then we want to go ahead and model it with a positive definite model. And so some general observations about variogram calculation and experimental variograms. And then we have the concept of using a nested set of positive definite, known positive definite variogram models that we can go ahead and fit and be able to, and the ones available to us include spherical, exponential, Gaussian, and nugget. That's what I've included in this method. There's less common ones like Hall effect, dampened Hall effect, and power law that I have not included. They're typically not used very often. Specifically, power law wouldn't be appropriate if we're doing simulation, or we would not honor the histogram, of course. And the concept of using geometric anisotropy, where we work with a major and a minor direction orthogonal to each other. So we just have to, in 2D, have a single parameter of azimuth of the major. The minor is assumed to be orthogonal to it. And we have this geometric anisotropy model where all we have to do is for each structure specify the contribution to the variance and the range of the major and the minor. And so we'll go ahead and we'll work with those, and I'll show you the result as we add those together and make a positive definite model. Okay, so GeoStatsPipe is the package that we're going to need for the variogram calculation and modeling. When I was teaching spatial data analytics last spring, I realized there wasn't a good Python option for the entire workflows of geostatistics and spatial data analytics. Not one that I felt was reliable and provided what we needed, so I ended up coding this up on the weekends, which was really fun, and I think it's great we have something. Let's go ahead, and the first thing we'll do is we're going to restart and clear all the outputs so that we have a fresh start here. There's no previous runs getting in the way, and we'll go ahead and import GeoStatsPipe. It has two components to it. GeoSlib is a bunch of visualization and like the GeoSlib programs, and also it has simple wrappers to run the Fortran. We're not going to do that. We're going to use GeoStats, which is the methodology which actually has re-implemented all of the algorithms like Variogram calculation and modeling in Python for us. So I think that's great. We're going to use a bunch of the standard type of packages like NumPy and Pandas for ND arrays, multidimensional arrays, and Pandas for data frames, matplotlib for plotting, of course, and then we're going to have IPy widgets for building interactive plots. At the very end, we'll do an interactive Variogram modeling. I like to set a current directory, know exactly where stuff is coming from, and then just read the data file. So if you want to work a sample data, multivariate biased, which is a perfectly good two-dimensional data set you could work with porosity and permeability data, you go ahead and download that from my GitHub repository, put it in your working directory that you'll set there, and away you'll go. So when you run this, if you get no error, oh, what did I do wrong? I do this all the time, and I know my students do too, so I kind of do it on purpose just to make sure everybody's recognizing that. It's a common problem. I skipped a block. Simple. The thing to remember about running a Jupyter notebook is until you've run the code, it hasn't happened. And so we haven't imported OS. And so when I run this command with OS to work with the operating system to change the working directory, I get an error, OS is not recognized. So go ahead and run that. Now the code works. You see that? So you got to run everything in sequence. I often tell my students, if you run into an error, back up to the beginning and run back through. Chances are you didn't run a block. That's the most common mistake I see among my students. Okay, so let's go ahead. We'll read in the data set from the comma delimited file, and we'll go ahead and put it as a data frame from Pandas. Pandas PD read CSV. We'll turn this into a data frame. DF is now a data frame. And to prove it to ourselves, we access for our DF data frame object the built-in function to do a preview of the first 5 or 6 samples up front, the head command. Okay, so yeah, 5 first samples right there, 0 through 4 are shown, and you can see the data that we just loaded. Now I should have mentioned I also have acoustic impedance, which is kind of cool in that data set. So it's a multivariate spatial data set. It's synthetic, you're free to just use it, don't worry about it. I made it using multivariate geostatistical methods. So it's a pretty good data set, you'll see. We could separate it by facies, but for this workflow, we won't. And the reason it's not too bad is because the facies do have spatial continuity and porosity and permeability. It's not like a system where we have a discontinuity between the facies. So it's perfectly fine to try to model the variogram between them. We would probably, if we were building a real reservoir model, we would probably maybe be more thoughtful about that choice. But for now, we're choosing simplicity and brevity of the workflow. So I hope everyone's cool with that. Let's look at the summary statistics. I love Panda data frames for the fact we can do that very simply. We can see what's going on with our data sets. The values look reasonable for porosity, good range of porosity. So we can go ahead and we'll do a normal score transform. The normal score transform is performed. It's turning the porosity, turning it into a standard normal distribution. Mean of 0, variance and standard deviation equal to 1. Now, we do that specifically because we're acknowledging that these variograms are going to be used for Gaussian methods like sequential Gaussian simulation. So for consistency, you have to work with the data transformed into Gaussian space, the normal score transform. Now, it also does help with outliers and provides, in general, cleaner looking variograms. So it's not a bad idea, and specifically driven by the theory, we should do it. Normal score transform is built into GeoStatsPipe. I like the GeoSlib normal score transform. I find it performs very well. And so I'm going to use that instead of a methodology available in other packages. So we go ahead and we can visualize the CDFs, original to transformed. And no surprises here. It really does. It was almost a Gaussian distribution for porosity, but now look at that. Beautiful S-curve, -3 to +3 effectively. It's an unbounded distribution, but we'll find, practically speaking, our samples will likely be bounded there. Okay, and if we look at the permeability distribution, we've gone from a very strong positive skewed distribution, probably getting close to log normal, and we've gone to a nice Gaussian CDF. Okay, so we've done our transforms. Now, if we want to try to calculate and understand the directionality of our spatial phenomenon, plus if we're trying to figure out how to calculate good experimental variograms, we really should do some data plotting in space so we can make good choices about lags, directionality, and so forth. Let's see. Maybe we'll even see directionality. Okay, so let's sit back, look at that data set. That's normal score transform and porosity. Let's focus on porosity. They're highly correlated with each other, as you can see by the cross plot, so we should expect similar spatial features, but we'll just focus on porosity for this workflow. Okay, high values are lighter colors, darker colors are lower values on the normal score, going from 3 to -3. And if you look at this, do you see it? Are you able to see the directionality? I can totally see the directionality right there. You can see about, if this is 0, 0, 0 in the y direction and azimuth 0, 9, 0 in the x direction, you can clearly see about 0, 4, 5 is a primary direction of continuity, that you have this high, low, high pattern. And so I would suspect that we'll see 0, 4, 5. So that's our ocular inspection approach to detect directionality. Okay, so we've done that. We can also do variogram maps, which are super cool. That's something that I've coded up to and added to GeoStatsPipe. And so GeoStats var map v, which works with irregular data. And we can load up the data frame, the x and y locations, the feature of interest. And all we have to do is specify the number of lags going from the center to one side, 11, the distance of the lags, so 50. So that means we're going to explore an offset of 550 from a center cell in the middle here of size 50. And so we're going to extend 550 over this way, plus 25 for half the distance across that cell in the middle. So there's a cell in the middle and then 11 cells going this way. It's a mesh. And then there'll be 11 cells going this way, 11 cells going up, up. So we're going to span from 0 to 550 plus 25, 575, down -575, and the same in the x direction, making a mesh. Then what we've done is we've used the basic contouring program after we've made the mesh and calculate the variogram values for each one of those offsets in the data set. And we've kind of contoured it up. That's why you see some of these weird shapes. Those shapes are not, it's just because we have sparse information here. We have 11 plus 11, 22 plus 1. We have a 23 by 23 grid, and we've just done some simple contouring between those values. Right here, it's a good idea to look at the number of pairs involved in each one of those cells. And you can see in general, if we have ill-informed cells getting towards the edges here, we have much fewer pairs to work with. So that might be a concern. You see that darkening color, but we're still pretty good. It really does look like we're always above 50 or 100 pairs. So we could look at the matrix, the two-dimensional array that came out from this variogram map, which would be NP, number of pairs map. And you could look at that 23 by 23 array, and you could investigate the values, make a choice on maybe you should remove some of these values using conditional statements. Okay, but I'm pretty comfortable. Now let's go ahead and sit back and look at that variogram map. What do we see? What's going on here? Okay, well, what do you think? Low variogram values, high variogram values. Sill is kind of an orangey color. So if I drew a contour of the sill, it would go somewhere like around here. 45 degree. Nailed it. Ocular inspection works. The variogram map is confirming it. And the range, if we want to pick the range off of this, I could go all the way to the edge of the variogram map and I still haven't reached the sill. I'm suspecting zonal anisotropy in that direction. I can go, probably I'm eyeballing it right now, 200 or so in this direction before I get to the sill here. Really guessing right now, but you know, it's good. It's giving us kind of some first evidence to work with. Okay, so I suspect our two-dimensional variogram will have a major direction in the 045 azimuth, and I suspect that we'll see about a zonal anisotropy in that direction, and the orthogonal, the 135 azimuth, I suspect we will see probably about a 200 meter range or so. All right, now another good way to detect directionality, and something we should do anyway because we're trying to model variograms, is we should calculate experimental variograms. Now going back to the data, you can confirm this, but if you look at it, you'll see that 100-meter spacing, and let's just go back here. 100-meter spacing would definitely get a lot of pairs. You could probably go to 30, 50 or so, but I think I found it got a little noisy. You go ahead and play around with it yourself if you'd like to try some things out. But I'm going to say a lag distance of about 100 meters, half extent of the data set. If I'm calculating the 45-degree direction or these other directions, I'd say I can go about 700 meters because I have about 1,400 meters across in the diagonal. And I'm expecting I can calculate reliable variograms up to about half the extent. So let's just say around 700 meters or so I'll go out, give or take. Okay, and in addition to that, I'll go ahead, I can set the lag tolerance as 1/2 the lag distance, but that's not necessary. I could actually increase that and cause overlap between the bins and further smoothing for a smoother result. I think I did that because it improved the results a little bit, but I welcome you to go ahead and try some differences. So I have a lag distance of 100 meters. I'm going to calculate 7 of those. Now with the program, it's going to go 0, 1, 2, 3, 4, 5, 600. Why don't we go ahead and just make that one more lag so we actually get to 700. Okay, and then we'll go ahead and we'll say no bandwidth because I'm not really worried about, getting too far away from that direction. And I'll put the azimuth tolerance pretty tight. We've got pretty dense data, so I want some good strong directionality. Now a great thing with working with Python is I make an azimat, which is just going to be a list of different azimuths, and I can run my program looping over those, and I'll calculate all the directional variograms going from 0, 22.5, 45, right here, 67.5, 90, 12.5, 135, and all the way back to, I don't need to do 180 because that'll be the same as 0. Variograms in general are going to be symmetric, so we're not too worried about that. Okay, and now I should have mentioned ISIL. In the variogram calculation program, you do have the option to constrain it to standardize the distribution to a variance of 1. Now we've done the Gaussian transform. I suspect it should be very close to 1. It doesn't hurt just to say, okay, it's kind of like a belt and suspenders. The distribution should be 1. I could check it right now. I'm sure it'll be 1. Then I could just say ISIL equals 0, but it doesn't hurt to standardize and make sure that the variance is exactly the 1. It's kind of a safe thing to do because if there is any deviation, what'll happen in the result is you won't reach the sill or you go above the sill. If the variance is less than 1, you'll have a lesser sill, and you might interpret it as zonal anisotropy when in fact it's just your distribution is wrong. Okay, so let's go ahead and we'll set it to 1 and force it to standardize. Okay, so run that block. Now what we're going to do is we're going to loop over all of those variogram calculations, and we're going to create this array right here will be the lag h offset. This will be the variogram values. This is the number of pairs. We have that for record if we need it. Now we're going to use a two-dimensional array so I can do all of my azimuths, all of those listed azimuths, and I can also run it so that I'm able to, this right here will be all of the lags, 0, 100, 200, 3, and all the way to 700. So we'll have those lags, and we can plot them. And when we plot them, we'll just say, well, we'll loop over and plot all of those azimuths, their lags. So we're sending, every time we do this command right here, lag IAZI, with this placeholder here, we're saying send the one-dimensional array for this specific row, which is that specific azimuth. One-dimensional array here, so we can plot that. And we'll go ahead and just say, well, add to the name the azimuth so we have a nice plot. Okay, let's go ahead and run that. Enough talking about it. Look at that. Isn't that awesome? I love working in Python. The coding is just powerful because I ran all of those directional variograms. Look at that. Azimuth 0, 22.5, 45. Okay, let's look right here. Range 300. Range 400. Range zonal anisotropy. Undefined, effectively infinity, really. Now, I wouldn't say it's infinity. I'm sure Walter's law is kicking in here, and at some distance we'll see it reach the cell. But over our study area, we don't see all the variability. Okay, 67.5. Oh, range is now 550. 350. Probably about 250. You see what's happening here? And then by the time we get to 135, about 250 or so. So it's fair to say that 45 is the major, And by design, it has to be 90 degrees, but it is consistent. 135 will be the minor, and it looks fine. It actually does look like it has about the lowest range. It's similar to these other directions, but I'm not worried about that. Okay, so now what we've done, now we did ocular inspection and we said the major looks like 45. We did the variogram map, the major looks like 45. We ran a bunch of variograms and the major really is 45. Okay, so now for this program, if you put your own data in, you've run all of these, pick the directions from the azimuth array or list that are the major and the minor. Now, if you come back up here, this is the 0 because remember, Python indexes its list by 0, 1, 2, 3 to n minus 1. So this is the 0 direction, the 1, the 2. Okay, so our major is the second one. Okay. Then we have the 3rd, the 4th, the 5th, and the 6th. So my minor direction is the 135, which is the 6th direction in the list. So all I have to do is for my workflow to work now and be able to build the models, I got to pick the major and the minor from these directions. And so I'll pick them. So 2 is the major, 6 is the minor. So down here in the code, 2 and 6. Once you've done that, you're set. The rest of the code will basically run automatic. And the first thing it's going to do, just to confirm for you, it's going to produce the major and minor plots. It's the same plots of above, but now this is our experimental variograms in the 2 directions that we're going to focus on for modeling. Okay. Now what we can do is we can use 2 functions built into GeoStatsPipe. So there's the make variogram function, not a big deal. All it's going to do is you provide the parameters for a variogram into this program and it makes a dictionary. I know it's so simple, but I've done it so it's kind of nice and canned. So you run this make variogram with all these parameters, it's going to make the dictionary. Okay, and that dictionary is going to be like an object we can now pass for visualization, pass for kriging, pass for simulation. It'll be nice, compact, standardized storage. The parameters, nugget, number of nested structures, you can do 1 or 2. If you do 1, it's going to assume no contribution for these second structure parameters. It's going to say the contribution 0 inside and it's going to have nothing. Now you don't even have to give these parameters. If you say nested structure 1, you don't have to actually list these parameters. It will default to 0 contribution. Okay, so we will have the type of structure. We have spherical, exponential, and Gaussian. Okay, we have the contribution. The contribution should sum to the sill. We're working with standardized variables. Sum of contribution 1 and 2 should be 1.0. The azimuth, keep the azimuth the same in, this is the azimuth of the major, keep it the same between the structures. You could do that. You could have different azimuths for the different structures. We're keeping things simple here for ease of interpretation and understanding. And in most practical circumstances, you'll find people will work with the same major direction and just have multiple structures that are consistent in that direction. The major range, now we have isotropic for the short scale variability structure, structure 1, and then we have 9999 for the major of the second structure. That's giving us zonal entropy and min of that. So this is our first model of the variogram that we just observed. This is a reasonable variogram model right here. Okay, so let's go ahead. We can put that into the make variogram function and we'll get that variogram dictionary that we can then visualize. The vmodel function is the same as the vmodel function from GeoSlide. It's there just simply to take your variogram model, that object called Vario, and to project it in a direction. Now, Vario is a 2-dimensional variogram model. So all we have to do is just tell vmodel what azimuth direction do you want to see the model? Do you want to project it? Now, it's not actually, it's working with the analytical model, so you can actually sample it at whatever rate you want. Okay, so in that direction, you give an X lag and you say sample it every 10 meters and do 100 samples, and that would give you a 1,000 meter long function. And so the program would actually give you the index, the lag distance at every one of those samples, the variogram value at all those samples, the covariance function at all those samples, and the correlogram at those. Wow, this is a 3-for-1 sale today for vmodel. Really, really great. Okay, so if we go ahead and take our reasonable model, These are the parameters right here. No surprises. I just set the azimuth for the first and second structure to be equal to the major direction. I major is the index 2 for that azimat, and so that'll be 45 degrees right there. And all of the parameters I showed above, I'll make the variogram object right here. Then what I can do is I can visualize 70 lags of it, and each lag is going to be 10. So we're going to see 700, 0 through 700, right? And we can plot that up. So we'll go ahead and make those variograms, plot them up, and woo, look at that. Awesome. Okay, so it worked. The make variogram made a reasonable variogram object that then was sent for display by the vModel program. And look, when we plot it, we see a nice function right here. Now, I have lots of students ask questions like, why did we worry about the number of lags and the X lag? So let me show you something right now. Let's go ahead and decrease the number of lags to 7, but we'll increase the lag distance to 100. Now we're going to sample 0, 100, 200, 300, and so forth when we make these variogram models. Now look at what happens. Do you see it? It's piecewise linear. So in other words, you're only sampled 7 points of the function. It's not going to look very good. So remember, this number of lags and X lag is not a calculation. We're not calculating variograms anymore. We're just projecting an analytical form. So this is just the resolution of that projection. Not a big deal. Let's go back to 70, and we'll go ahead and make the lag distance 10 again. And we get something nice and smooth. We can understand it. And so that's it. Just make it smooth enough. And it runs super fast. Like, it wouldn't hurt. Like, you could go ahead and say 700 and lag distance 1. And look at that. That's going to be every meter sampled. And it didn't really change much. You know, if you have 10, that's probably pretty reasonable given the ultimate range of this problem. Now, if you're working very short scale phenomenon, you're going to need tighter sampling. Not a big deal. It's just display. Now what we're going to do is, I'm not going to walk through this because this workflow walkthrough is not to teach you IPy widgets and how to do this, but I hope you can look at my code and get some ideas of how to do this, which is super awesome. It's going to take that same plotting we just did, but take all the variogram parameters and turn them into sliders and selection toggle boxes or selection boxes so that we're able to go ahead and automate that process just now. Okay, so let's go ahead and run that. Now we get down to it. This display is now going to display our interactive display. So here it is. Okay, so let's scroll that up. We know these parameters now. We got nugget effect, the first structure, type, contribution, major range, minor range, and the second structure, the same thing. Now notice there's no azimuth here, because what this model is going to do, it's going to take your major direction and assume this is aligned with that. Okay, so we don't even have to put that in now. Okay, and it's going to automatically display it in the major and minor on the plot. Okay, now I've set it so that as soon as you change something, the plot's going to appear. Okay, so we have the plot now. Now, I think it would be fair to say, and given my experience of what we've already done with this data set, we could probably start off with like a 50% contribution, or 0.5 for the first structure, 0.5 for the second structure, but our ranges are all 0. So this is the major, this is the minor. Ranges are all 0, so it all looks like really effectively nugget effect. This jumping up right here is at 10 meters, the first sample on the vModel. If we'd sampled every meter, this would go up to just 1 meter. So you see, it's just a resolution issue that we see this jump here. It should actually be the nugget effect. You know, the range we used here is 0.01, so it should be up there immediately, right? Now you might wonder why I defaulted it to have a minimum range. It's because of numerical issues with my code. If you put zeros in, I use anisotropy ratios inside the code, and it causes divide by zero errors, so we're just avoiding that. Okay, so let's go ahead and make our minor about 300, and that's what we found worked pretty well before. Now look what's happened. We now have a nugget effect of 0.5 because this right here has no range, and we have about 300 isotropic right there. Let's start to give this some range too. We're going to say the minor about 300 also. Okay. Now look what happened in the minor direction. That's looking pretty good now. You see that? We're starting to get a pretty good fit right there. And let's go ahead and set the major. Watch this. We want zonal anisotropy. Let's make it big. What happens is I keep making it bigger and bigger and bigger and bigger. You see what's happening? Isn't that cool? It's leveling off. Okay, so let's go, go big or go home, right? Let's like make this pretty big. Okay, that right there, take it all the way up to 10,000. Wow, that's starting to look pretty good. Now, one thing we could do is we could say, well, let's tweak the first structure up a little bit to bring the zonal anisotropy up. We want more contribution of this component right here. And so we go ahead and say, make that 0.6. Now, look, this is doing better, but look, we're now above the sill. The reason being is that the sum of 0.5 and 0.6 is 1.1. We're modeling to 1.1. So let's go ahead and drop that down. Now the contribution is 0.4 for that structure. We have 0.4 here. We have 0.4 for this component right here. Now in the minor direction, we have 300 and 300 spherical both. So it's effectively like a single 300 meter range spherical. And so that's why we have that nice continuous shape. Now, of course, if I was to increase this range on the second structure, you notice how we have an inflection point now? Because now we have a long range spherical plus a short range spherical resulting in this result. Okay, so effect. Okay, so I think we've done a pretty good job modeling that variogram. Now, maybe you'll say, well, I think there should be nugget effect. You could decrease that contribution there, and you could now get nugget effect. Now you probably want to play around with this too now and fix in the minor direction. Now maybe you want to kind of get a little more technical in the short range. Maybe you think now that there's a bit of a Gaussian structure here. So what you could do is you could say that first structure is Gaussian. Look at that. Look at that. And maybe you shorten up the range a little bit like that. Look at, so now we're getting that kind of Gaussian shape to the first structure, causing that kind of rise. We could remove the nugget effect. We go ahead and add the second contribution back up. Look at that. That is starting to look pretty sharp. Now, I wouldn't be super excited about using the Gaussian. In porosity, typically you do see something more spherical exponential for spatial continuity. Gaussian is commonly used in cases of topography, thickness of beds, things that you really know should be strongly continuous. So one thing I haven't talked about here, which I think is something kind of special, is the fact that we have taken the major direction, the variogram model, projected in the major direction, we plotted it right here. We took the minor direction, the variogram model, projected in the minor direction, and we plotted right here. And look at what we did. I think this is awesome. Is we incremented between the major, so 45 is the major, 67.5, 90, 112.5, and then 135. And so you can actually see the geometric anisotropy model. We had modeled the major and the minor, and then the model geometric anisotropy with the two structures was able to interpolate between. So now we have a variogram model that works for all directions. Here's a bunch of different directions, and for all distances right here. So we can calculate the variogram between any pair of data in space. So therefore, we can also calculate the covariance function, the parallelogram, and we can solve kriging and simulation and lots of estimation problems. So it's very powerful stuff. Okay. That wraps it up. That was the interactive demo. The cool thing is you can use this to load up any data set right there at the beginning, calculate a bunch of different directions, pick the major minor direction, and now model the major minor direction, all in Python, nice and interactive. And you'll have the parameters right here that you can go ahead and record and use in any other software, or you could use these models directly with the variogram model dictionary, and apply that to GeoStatsPipe, kriging, and simulation, and so forth. So we have calculated and modeled a consistent spatial continuity model that's positive, definite, can be used for all kinds of purposes. Okay, as always, I hope that this was helpful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and conduct research in data analytics, geostatistics, and machine learning, spatial statistics, and so forth. And everybody stay safe. Thank you.